So we've been doing a lot of work at APL in the laboratory for spectroscopy under planetary environmental conditions, or lab spec for short. It's much easier to say that way. Looking at various lunar characteristics in the ultraviolet. And this is one of the areas that we've been looking at. So we've started looking at a Plagioclase series. It's from the UCLA group, and it was first studied by Ben Greenhagen for his dissertation. He characterized it in the thermal infrared. And later, Carrie Donaldson-Hanna and her group, including Bridges, looked at it in the thermal infrared, but also did some compositional characterization. This data set has compositions ranging from albidic out to AN76, so it spans quite a large range. And they have two size splits that are listed there. So everything that we've looked at has been the smaller size split. We do intend to look at this larger size split in the future too. The nice thing about this set of Plagioclase is that they vary in their iron content from 0% weight percent FeO up to 0.5 weight percent FeO. This FeO content is very important for lunar studies that are related to ferronornithites. And I have a picture of a beautiful ferronornithite there on the right. These are thought to either represent original flotation crust or layered Pluton emplacement on the moon. So there's one more sample that we've added to the group, and it was actually previously studied by Bridges et al. It's the Miyakijima North anorthite, and it's derived from these anorthitic megacrusts that you see there on the right in the basaltic material. They were previously separated from the surrounding basaltic coatings, and the coatings was crushed and sieved to the 2 particle size, or to less than 32 microns. Bridges et al. Did study a related sample, and it has an AN content of 97. So this is excellent match to the moon, and it has a half weight percent FeO. So Bridges pointed out that it's an excellent analog for the Plagioclase present in the fans. And I just want to point out that everything else we're looking at has a slightly larger size split. So we are collecting spectra at in lab spec under high vacuum, so 10 to the minus 6, 10 to the minus 7 torr. We collect our UV data using a McPherson monochromator light source with a scintillating material in front of a PMT tube. And we also can collect vis near IR data and mid IR data, as I show there. I'm not going to show that for this particular test, but then we can make a sort of large spectrum that goes from ultraviolet out to the mid infrared. And this was the result of for 4 samples. So it includes the anorthite from Miyakijima volcano, a labradorite, an andesine, and an albite. And you'll notice that in the near UV and vis, out past about 350 nanometers, they have a very similar slope. There's some variation in the overall reflectance, but otherwise they look pretty much the same. However, when we look in the UV, there's some variation going on there. Let me get the pointer, hold on. So you can see that we have a really nice absorption here in the anorthite, labradorite, and andesine that is not present in the albite. And that absorption is centered at about 250 nanometers. And if I give you a little bit more information, you will understand that this is related to the oxygen metal charge transfer absorption. So the albite lacks FeO, whereas the other 3 contain between 0.4 and 0.5 weight percent FeO. So it's present to due to the presence of FeO in those samples, the UV is extremely sensitive to low abundances of iron in samples. So even though it's less than 1 weight percent, we can see it. So will be really useful when we're trying to look for fans and things like that. I also scaled the spectra because I was wondering if there was any influence for the composition of the Plagioclase, the calcium to sodium ratios. So I scaled them all to the same value at 350 nanometers. You can see that the location of the OMCT band is extremely consistent, despite a large range in the AN number. So it doesn't shift due to compositional changes in the plagioclase, except for the presence of FeO. So it's very consistent, and it may help us to distinguish iron-rich plagioclase samples on the moon. So we've only gotten a few of these samples collected so far. You can see that we have a nice list there. We are currently installing a new UV system in lab spec, and it will allow us to collect UV spectra a lot faster. The old system took about 3 hours for a single spectrum. So we're excited that we're going to have this new system that works much faster and gives us really good data. So our plan is, once we get that installed, we're going to collect new UV spectra of all the samples, including the ones that we already have collected and the other grain size splits that we have. And we're also looking to add a few more plagioclase samples. So if you look at the andesine sample listed there, it's not really an andesine, and andesine has an AN value between 30 and 50, so that one's has a little bit too much. So we've found some appropriate samples, and they also have variable FeO in them, so they are really interesting to our study, understanding the effects of FeO on these spectra. So the first thing we're going to do is verify the composition of those samples, and then we're going to make size splits similar to what we already have for those. So, and I think that's it. Yes, it is. And I'm happy to take any questions. All
right, wonderful talk. Thanks very much. So we do have time for a question or two. Are there any in the room? No, perfect talk. Any online?
Nothing online.
I guess not. Haven't heard any online.
Okay.
Don't see any online.
I had extra slides on this, and I took them out but they were looking at, we've also looked at space weathering in the UV, and it's quite the interesting story. So you're not supposed to have a favorite child, but right now in spectra, this is my favorite child.